Okay, let's start with a couple of announcements. So I have some homework from last semester that you haven't picked up. So if I didn't give it to you just now, then please come at the end of class and get it. You saw the homework has been posted, and the forum is online. So please use it. Don't be shy. Yeah.
When I checked the homework, it said that more problems were to be posted. Did you post those yet?
Yeah. So now the full homework is posted. It's all there. Yeah. Use the forum. I think it's a very good place for discussions to help each other out with these concepts. And let me take a poll. So who is confused by tensor products? Yeah? Who is scared of tensor products? Okay. So a good number of you, which is natural. I think that tensor products are confusing and a little bit scary when you first see them. So Julia posted this little article on the blog, which is called, what is it called? How to lose your fear of tensor products. And I mean, it's kind of long, but it goes down through like a total long justification of why tensor products should be considered and how do you compute with them, and it goes into a lot of detail. So that's something that's useful for you to check out. I guess I should ask you, how many of you had seen tensor products before coming here? Or maybe how many of you had not seen tensor products before coming here? Okay. So I think because tensor products are naturally a little bit confusing, one thing that I want to do today is review a little bit about that, okay? And just get used to working with them and how to prove theorems about them, etc. Okay? And so I have two goals for the class today. First is to go back to algebras, and I told you I was going to give you 3 definitions of algebras. I've given you 2 so far, and I'm going to give you the third one. And the third one is going to involve tensor products, and that's going to lead us naturally into a review of tensor products. Okay? Did you have a question?
Yeah. Actually, how do you denote a zero? Because I understand that like a 0 tensor 0 as well as the v tensor 0 are both zeros in the tensor products, right? Then how do you denote 0 in the tensor product?
So the question is, if you have a tensor product like this, how do you denote the element 0? Thank you. So you can denote it in several ways. So for example, we could just write 0, and that will be the 0. But then this will be an equality. So 0 is going to be equal to 0 tensor 0. Because 0 is in V and 0 is in W, and you can show that this element is the 0 of this vector space. You can also show actually that this is equal to 0 tensor W for any little w in big W, and it's also equal to V tensor 0 for V tensor.
So you solve like a 0 category, 0 bar.
I'm going to talk a little bit more about notation later on, but for now let me just say that the 0 element, usually you just denote as 0 like we do in vector spaces, but all of these things are equal to 0. Okay? And yeah, if you don't see immediately why this is equal to 0, that's a useful exercise to think about. Okay? It's not obvious, but it's true, and it's not too hard. Okay? Okay, so like I said, first I'm going to talk about algebras, and then we're going to go into tensor products. Okay, so let's talk about K algebras, and I'm going to agree with Seth that actually I was getting kind of tired of using lowercase k, and I'm going to use. I mean, you should be used to the fact that some people use lowercase k, but I don't know. Somehow this is a little bit more satisfying to me, so I'm going to use uppercase k. K algebras, okay? So remember the idea is that a K algebra is something that is a vector space and a ring. and a ring simultaneously. Okay, and so I gave you two definitions last time, of which we saw that the second one was a little bit more general, and we're going to remind ourselves what it was. So a ring A with an element 1 is a K algebra if there is a ring homomorphism U from K to A such that U of K is a subset of the center of A and U of 1 is equal to 1. U of 1 of the field is equal to 1 of the ring. Okay, and in the forum you will see examples showing that several of these that these conditions are necessary. I don't think we've covered every possible example that I asked for, but there are some examples, and you can fill out the other ones. But then the thing to remember, the thing to realize about this is that we start with a ring. Okay, so we're beginning by declaring that A needs to have a ring structure. And I explained to you that by these conditions we also get a vector space structure. Okay, so recall A becomes a vector space over K where scalar multiplication. Okay, so lambda is a scalar, and A is an element of this supposed vector space. Well, what do you need to have a vector space? You need to know how to add elements, and we do know how to add them because A is a ring, it has addition, and we need multiplication by scalars. Okay, so to multiply by a scalar, what I do is that I just see where U goes here, and I multiply by that. Okay, and because this is in K, then U of it is in A, and I multiply in A. Okay. This is notation, but in every example you will see right away what the vector space is. Okay, I think writing this out is more complicated than actually seeing it in any example. And so what we get is something that is a ring and a vector space at the same time. Okay. So, and we saw a couple of examples. For example, we saw that the polynomial ring, well, let me say, if I let A be the polynomial ring and U well, here K really lives inside the polynomial ring in a natural way, right? Because the constants you can think of as polynomials, and so this is just the inclusion of K inside K of X. Okay, this is the obvious map. And so we saw that this was an example of a K algebra. Okay, so K of X is a vector space over K, but you also have a multiplication. You can multiply polynomials. Okay, so that's the first example that we saw. And the second example that we discussed, well, I think I also wrote that you can use a larger number of variables and use polynomials in more variables, and that's also going to be an example. But a more interesting example is if we talk about the n by n matrices. Okay, because then we saw that K is not a subset of this, but we can kind of make it be we can kind of embed K inside A by taking a constant and sending it to, we need to send it to a matrix, right? And we want it to be a matrix that behaves at the scalar lambda. And so what we do is that we just do lambda I. Lambda times the identity. Lambda, lambda, lambda. Okay? And so this does satisfy that U of anything is in the center because these matrices commute with everybody. U of 1, U of the number 1 is the matrix I, which is the 1 of that ring. And so everything is satisfied in a little bit less trivial way. So here U is actually doing something. Okay? So these are two kind of motivating examples here. Okay? Let me just make some observations about K algebras. Maybe the first thing I will say is that if I can also define R algebras where R is a ring in the same way. Okay, so what I do is just put an R here, put an R here, and R should just be in any ring, a ring with a 1. Okay. Okay. So the definition of R algebra is going to be the same, where R is a ring instead of a field. Okay. But one thing that I mentioned last time is that, and Stephen proved it in the forum, is that under these conditions, U actually has to be injective. Okay? But in this situation, U does not need to be injective. Okay? So it's a little bit different because in this situation where when you have a K algebra and K is a field, then you're really finding a copy of K inside your ring A. But in this situation, we're not finding a copy of R inside the ring A. We're finding kind of something that is a homomorphism from R to something. It's the image of a homomorphism, but that might not be R itself. Okay? The next thing I want to say is that I told you that K algebras you can think of as a vector space and a ring simultaneously. So how can we think of R algebras? Well, what is the analogous of a vector space? It's a module, right? So R algebras are going to be the same thing as R modules and things that are R modules and rings simultaneously. R module and ring simultaneously. Okay. And so I say this so that you see it, and I think if you look up on a lot of books about algebras, you're going to find everything said in this context. Okay. But I don't know. I'm trying to keep the class as elementary as possible as we start. And so I want to start, and for the most part, we're just going to do algebras over a field, which are a little bit easier. And just remember that if you ever want to do algebras over a module, then with a little bit more care, things work. Okay? So these are just some parenthetical remarks. Okay? Okay. Now, in mathematics, it is always a very useful thing to remember that you don't just want to think about objects, you want to think about how they're related, right? So you don't want to think about individual objects, you want to think about how you map one object to another object, okay? So we want a notion of homomorphism of algebras, okay? So what is that? So homomorphisms let's think about it. What should so let's say that we have the A1 and A2 are K algebras. What should a homomorphism be? It's a map satisfying what? So basically what we wanted is to, I mean, we've done this many times with groups, with rings, with modules, and so we know what this should be. Basically, this should be a map that preserves the structure of a K algebra, okay? Now, what is it to be a K algebra? Well, it's to be a vector space and a ring. Yeah?
But should it be a linear transformation and a ring algebra at the same time because it is a vector space and a
right.
ring
So because a K algebra is a vector space and a ring, that means that should be a homomorphism of vector spaces and of rings. Okay. Now, a homomorphism of vector spaces is just a linear map, right? If you want to map a vector space to another vector space, that's just a linear map. And so we should make sure that this map is linear. So what that means is that phi of A plus B should be equal to phi of A plus phi of B, right? And to be linear, you also have to satisfy that you behave well under multiplication by scalars. So here, A and B are in the algebra, and here A is in the algebra, and lambda is a constant, a scalar in K. So that makes you linear, that makes you a map of vector spaces. But I want this to also be a map of rings. Okay, so what else should I demand? Well, I should demand that phi should also keep the ring structure. In other words, it should preserve multiplication. So phi of AB should be equal to phi of A, phi of B for A and B in A1. Anything else? Yeah. And this needs to, yeah, so phi needs to send 1 to 1. I don't mean that phi is 1 to 1, I'm saying that phi needs to send the one of the first one to the one of the second one. Yep.
So since K lives inside these algebras,
Mm-hmm.
in the centers, couldn't we just replace axiom 2 and axiom 4 by just saying that phi sends lambda to lambda for all the lambdas in K?
There might be easier ways of writing this, but I think this is, from my point of view, this is the best way to write it because this is, it's a homomorphism of linear spaces and of rings, okay? And you might be able to simplify this a little bit, but let me just write that definition. Okay? So that's a homomorphism. As we've done in algebra many times, it's just a map that preserves the algebraic structure that you want it to preserve. Okay? And what do you think comes next? We're gonna start, substructures, isomorphism theorems, etc., quotients, etc. Everything is gonna work out really, really nicely, and you're used to this, so I'm gonna go through this kind of quickly. Okay, so let me just make some observations about this. So constructions / observations. what should a subalgebra be? It should be a sub in both sense of the word. It should be a subspace and a subring. Subspace and a subring. Okay, so we have a notion of subalgebra. That's good, and that's one of the constructions we like is subobjects. Now the other kind of thing that we like is to take quotients. Okay, so so I want to take a mod I, and I want to say that that's a quotient. Now, can I do that for any I? Or what conditions do I need on I so that I can construct a mod I? It needs to be a quotient subspace, a quotient space, and a quotient ring. So what do you need to take a quotient a mod I as a subspace? You just need I to be a subspace. Yeah. And, okay, so I is a subspace. And what do you need for a mod I as a ring? You need I to be an ideal. Okay. And you're going to find that if you're an ideal, then you're a subspace. Okay. And so really all you need is that if I is an ideal, then you can take the quotient. And that quotient is naturally going to be a K algebra. The quotient algebra. Okay.
So just to clarify, right? The subspace condition it follows naturally from the ideal condition.
Yeah. So if you're it's implicit here that if you're an ideal, then you are a subspace. Is that true? That's good for the forum. That's precisely the kind of thing. And I mean, every one of these little things, when you sit down and you check it, you're going to understand this a lot better. If you just believe me, then okay, it sounds reasonable. And then when you check the details, you're going to find that it's true, and you have to think about it a little bit harder, and then you're going to find that it is true. Okay, so all you need is to have an ideal, and then you can take quotients. Then once you take quotients, and if you have homomorphisms, then you want to ask yourself, okay, what about the isomorphism theorems? Okay. And those hold. And why do they hold? Because isomorphism theorems exist both for vector spaces and for rings. And this is just keeping track of both things at the same time. So if phi from A to B is an algebra homomorphism, is a K algebra homomorphism, then what I'm going to have is that the image of phi is going to be isomorphic to A mod the kernel of phi. Okay? And there's something implicit there, right? Which is that this quotient can be taken because this is an ideal. So let me say then, the kernel of phi is an ideal. And the first isomorphism theorem holds, and the other ones do as well. But this is the most useful one. First isomorphism theorem. Okay. And again, at this point you've built up enough knowledge of algebra that you should hopefully believe this and feel confident that if I ask you to write down the details, you can do it. Again, the point is that This is true for vector spaces and for rings. Okay? And therefore, algebras inherit it. Okay? And it's also true for modules, and so that means that our algebras inherit it as well. Okay? Okay, so we take quotients. What else should we do? Well, another kind of construction that we like to do is direct products. So if A1 and A2 are K algebras, then the direct product is also a K algebra. And again, the reason is that the direct product inherits the vector space structure and the ring structure. Okay. The direct product, and it's also an algebra. And we're going to get more used to this. When you have two things, you also want to take their tensor product if you can. And you can do that too. Okay? And the reason for that, again, is that when I define tensor products, I define them for vector spaces, and I told you that they also work out for rings. And therefore, you can take it to that level as well. Okay? And I promised you that I'm going to talk more about tensor products. I will do that later today. But these are kind of, this is a toolkit of constructions that you have available to you to build new K algebras from old K algebras. Okay? Any questions about this stuff? Yep.
So you're saying that the direct product and the tensor product that are both K algebras as well.
Yeah. They're K algebras as well. And this is also the quotient algebra. Well, from the name you can tell that it's an algebra. And subalgebras are also algebras in their own right. Okay? So this is general stuff that I'm going through very quickly because you've seen it at least for groups, for vector spaces, for rings, and for modules. So given that you've seen this 4 times, I'm not going to put you through it a 5th time. The proofs are identical. Okay, but are there any questions about what any of this means? Okay, so now what we're going to do is that we're going to introduce the 3rd definition of a K algebra. And this should look familiar and very different. Okay? It'll look familiar because you saw it the first day of class, and it'll look very different because you'll see that it really seems to be talking about something totally different. But as you can imagine, we're not talking about something different. We're talking about the same thing in a different way. So we're going to say that a K algebra is a K vector space A which has linear maps M from A tensor A to A and U from K to A such that these diagrams commute. Okay. And maybe you haven't seen what it means for a diagram to commute. I will tell you. Okay. So there's two diagrams that need to commute. Let me see how I'm going to fit them here. So here, every one of these things is, well, in this case, a vector space. Each one of these things is a vector space. Each arrow is a map from one vector space to another one. Okay. So let's think about what this is.
Associative law, right?
We'll see. Yeah, I mean it is. For example, let's look at the bottom right here. Okay. So what I'm saying here is that M is a linear map that goes from A tensor A to A. In other words, I'm talking about this linear map. Okay. And if you look here, I'm talking about the same linear map from A tensor A to A. Okay. Now, what am I talking about when I say from A tensor A to tensor A, go to a tensor A? Okay. And the map is M tensor identity.
Should just take the tensor product of the images?
Well, so I'm mapping something here to something here. And so what I do, given that I have this tensor this, is that the first two entries get M. So you use A tensor A, you use M to send that to A, and you use the identity to send A to A. And that's the map. And similarly, here, it's the same thing but backwards, right? So A gets sent through the identity to A, and A tensor A gets sent through M to A. And so those are the maps of this picture. Okay? And I'll write them again in a second. What does it mean to say that a diagram commutes? Well, you see that you have two different ways of going from here to here. You can take an element of this vector space, map it this way and map it this way, or you could map it this way and then this way. And to say that the diagram commutes means that it doesn't matter if you go this way or this way, you're going to get the same answer. Okay? So, yeah.
Is there a special notation for that? Because I've seen you did maps and make some squiggly arrows.
So, yeah, so sometimes you'll see people put a little curly arrow to indicate that that diagram commutes. And sometimes you'll see people drop it. So I'm saying the diagram commutes, and so because I said the diagram commutes, then I don't need to do it. Okay, so that's one diagram that commutes. Okay? And think about what that means while I continue doing this. Okay? Now the other diagram that needs to commute looks like this. This is M. This is identity tensor. I mean, for example, how could you map A tensor K to A tensor A? The most natural map is to say, well, given that you're mapping a tensor product to a tensor product, maybe you send the first coordinate to the first coordinate. And to go from A to A, the most natural map is the identity. And how do I map the right coordinate to the right coordinate? Well, I have a map from K to A, which is U. So that's what I do here. And similarly, this one should be U tensor the identity. What about from K tensor A to A? That's actually, I don't have anything immediately obvious to do here. So I'm gonna show this in a second. I'm gonna show that actually there's a natural isomorphism here. I'm gonna show that these two things are actually the same thing. I'll prove that. And I'm gonna show that these are the same thing. And there's a natural isomorphism that needs to go there. Okay?
So doesn't K is a subring with respect to A, right? K lives inside.
A copy of K lives in A.
Okay.
Uh-huh.
Are we just using M there?
Basically, we'll see. I'm gonna prove this isomorphism. So what does it mean to commute here? It's a little bit different. Well, you kind of basically when you have this is called a commutative diagram, and a diagram is commutative if whenever you follow two paths from one vertex to another one, then whether you go this way or this way, it should be the same thing. Okay, so well, just like so Nino suggested that I use this notation, and let's do it. What should I do here? Well, you see there's a couple of ways of getting from one place to the other one in the same way. For example, you can map from here to here, or you can go directly through here. That should commute. Okay? So if you take an element here and you send it to here, it should be the same thing as if you take the direct path. Okay? Yeah?
And since you said that's an isomorphism between K tensor A and A, then why doesn't the arrow go both ways?
It could. I mean, this is an isomorphism, so it's kind of a reversible arrow. It's just, I mean, it's usual to write it like this because this map is. Anyway, I mean, you'll see when I write this isomorphism exactly what I mean here. There's another thing that commutes here, which is that you can go this way or you can go this way. And so I put an arrow like that to indicate that. Okay? So that is the definition of a K algebra. Linear maps satisfying these conditions. Okay? And this map is called multiplication. Multiplication. And this map is called unit. Okay? So, is it clear what I wrote here? I mean, with two questions. Is it clear what I wrote here, or are there any questions about this definition? Yeah?
In the line of the notable and straight in, I see another, in the example before, you make one move, like.
So you're talking about this one?
Yeah.
Mm-hmm.
Are you saying you can go straight from here to there, that this
Yeah, so if I need to go from A tensor A to A, I have a natural way of doing it, which is to use my map M. And that's the one that I'm using. What should not at all be clear is why this is meant to be equivalent to this. Right? These look very different from each other. Did you have a question, Krista? We'll talk about triple tensors because this is the first time I talked about double tensors, and this is the first time you see a triple tensor. So we'll say more about this. Yeah. Let's see why. I mean, then to some extent, this is kind of an aesthetic choice. Some people are happier with this. Some people are happier with this. Let's take a vote. You have to choose which one you like better. Who likes this better? You have to vote. Who likes this better? Wow, really? Okay, so more of you like this one. Why? Huh? The diagram, you like it looks pretty? It looks nice? Okay.
I'm less familiar with it, so I feel like I have more chance to learn using style that I haven't seen as much of.
Okay.
Sorry,
Yeah.
how do you show that these two explanations are actually further, and we'll talk about the same thing.
I'm about to show this. So I'm going to show you these two things are the same thing. And then we'll see some of the merits of this one over this one. And I mean, that doesn't mean you should forget about this one. This is useful too. But we're going to see that this, which maybe is a little bit unfamiliar, is actually also very useful. Okay? So this right here is called the associative law. So let's think about why that is. So this says that multiplication is associative. So why is that? Why am I saying that M is associative? Well, I'm saying this diagram is commutative, so let me take an element here and map it both ways and see what I get. Okay. Now, what does an element here look like? Well, it's a sum of pure tensors. Now, these maps are linear, and so sums are fine. If I check this, if I take a pure tensor here and I send it this way and I send it this way, and I get the same thing, then the same is going to be true for sums of tensors, because everything is linear here. Okay? So let's take a pure tensor here. What is that going to look like? Well, a pure tensor looks like this. So when I map it this way, what am I going to get? M tends to the identity, so M takes the first two things and multiplies them. Whatever multiplying means, we don't really know, right? Well, all we know is that there's a function M of actually, see, M goes from A tensor A to A. So what this is going to do is take the first two and apply M to them, and then this. Yeah?
Is a pure tensor the equivalent of like a generator of the algebra, or like a basis of that vector space? Is that what I'm trying to...
So the pure tensors definitely generate this, but they're not a basis. Because there might be, for example, we talked about how two pure tensors might actually be the same, even though it's not obvious why they're the same. Okay. And we'll see some examples of this in a second. But yeah, so it is a generator because every element here is a sum of these guys, but it's not. This is not a basis. And I'll say more about that. Okay. Actually, okay. So what happens when we go this way? The first entry stays alone. And then the second entry takes B and C and multiplies. Okay. Okay. Now what happens when I take this guy and I map it down? I get this, the multiplication of this and this. Right? What happens when I take this guy and I map it forward? Well, in principle, I might get something different. So let me... Right, because what I get is the multiplication of A and the multiplication of B and C. And what I'm saying is that these two should be the same. For this diagram to commute, this should be equal to this. Okay? Now, if in the back of your mind, I mean, there's a lot of M's and tensors and everything, but if you just think that you're just multiplying things here, if you think of this as multiplication, then what I'm saying is that, I mean, here you should really be thinking this is A times B times C, right? And this is A times B times C. And so this is just a very fancy way of writing that this multiplication map M is associative. Okay. Yep.
So we talked about a couple class periods ago how you have things that can't be expressed as a pure tensor, right? Whereas, so like when I look at this formalism with the tensor notation, like I'm sort of forced to consider things as inputs for my multiplication that don't look like pure tensors. Right? Whereas when I just think of multiplication in the normal sense, where I just sort of like write out terms that I'm multiplying together in a list, I don't immediately see what the equivalent is to a non-pure tensor in that notation.
So again, I'm going to ask you to bear with me for a few minutes, because I am going to talk, I want to show you the equivalence of these things, and then I really want to talk about tensors and really go into it, okay? And then I think we'll address that question pretty carefully, okay? I just want to explain what these things are about and why they're the same, okay? What does this other funny condition say? Again, let's take a generator and take it around. Okay? So what does an element here look like? An element of K tensor A. Well, a pure tensor looks like lambda tensor A. That's one of the generators here. Now remember, this is a tensor product, so I can move scalars around. So lambda I can write as lambda times 1, and then take the lambda to the other side. In other words, I can write it as 1 tensor B. Okay. Every tensor lambda tensor A, every pure tensor I can rewrite as 1 tensor somebody. Okay. And it's just going to simplify my notation a little bit. Okay. So let me just start with 1 tensor B and take it around. Now what 1 is this? I want to be careful. This is the 1 of K, right? Because it lives here. Okay. So I'm going to take 1 of K and tensor it with B. Yeah? Somebody had a comment over there, question? Yeah?
But isn't A itself is a K-bar space, so actually lambda is just never mind, sorry.
So I take an element here and I'm going to map it around. Okay? So I think that this guy is living in here. Okay? Okay. What happens when I send this up? K gets mapped to A through the map U. Okay? So what do I get here? I get, well, you're saying 1 of A because you're assuming that U of 1 of K is equal to 1 of A. But the thing is that that assumption was in definition 2. That assumption is not here. So really what I have here is 1 of K, because nowhere in this definition do I have that 1 here goes to 1 here.
It's going to come from the diagram.
And the point is that it's going to come from the diagram. Yeah. U of 1K tensor B. Okay. What then, when I map this down, what do I get? Well, this is just multiplication. So let me just, I think it's going to be cleaner if I just switch to this informal notation of product. And what I'm doing is multiplying U of 1K times B. That's what multiplication does. Okay. And what is this homomorphism? Well, as Zach said, just multiplying by this constant, and so here I'm just multiplying 1 times B. Okay, this is B. And so really what I'm saying is that
assumption of how that multiplication works is sort of based on the left-hand definition.
Uh-huh.
Right?
Uh-huh. I mean, this.
We're not making the assumption that 1 of k is somehow associated with 1 in A, then.
I mean, let me just say very simply that the isomorphism between k tensor A and A is the one that sends one tensor B to B.
Okay.
That's the isomorphism. Okay. All you have is this one that's in your left and it's not doing anything, and you're just kind of dropping the first coordinate. So you get B on this side. Okay. And so when you go around, you get this. When you go this way, you get this. And so the condition is that B should equal this. Yeah? So what is this really saying? I mean, this is true for any B. So what this is saying is that this guy is a left multiplicative identity. Yeah? And what do you think happens when you go to the other side? Oh, let's see. You get the same thing, but I mean, so if you do this one, then what you're going to find is that B is equal to B times U of 1k. Okay? And so really what I'm saying is that U of 1k is a multiplicative identity on the left and on the right. In other words, that it's the yeah, well, anyway, what I said, okay? Yep?
So what I would note as one disadvantage of the diagram definition is that it takes a lot of ink to say U of 1k equals 1a.
So, yeah, I mean, at this point, you might be, there's parts of this you should be happy about, there's parts of this that you should be unhappy about. We're going to go back and forth, and as we get used to it, we only have to do this once, and now we know that this, I mean, we'll see these things are equivalent, we don't have to prove it again.
And it's even worse when you're teching.
Yeah, I mean, to draw these things in LaTeX is really kind of painful, to the point that a lot of books don't do it, and it's really annoying, because when you read books, very often you can tell that what they're thinking is this, and what they have in their handwritten notes is this, and they just don't really want to put this on LaTeX. And they don't draw the pictures, and I mean, it really is like this. But anyway, so unitary says how this is a multiplicative identity. Okay, on the left and on the right. Now, one thing you should see about this is that. Okay, so basically, it looks like we're about to define a multiplication that is associative and has a multiplicative identity. But have we actually defined a multiplication on A? Let me point out something to you, which is that here I underlined ring and I underlined vector space. Okay, in definition 2, we have a ring and a vector space. What do we have in definition 3? Do we have a vector space? We have a vector space. Do we have a ring? Not yet. Not yet, right?
Vector space comes equipped with a notion of addition. So we've got that.
We have the addition coming from the vector space. What do we need to make a ring out of this? We need a product. So how are we going to define a product? Well, that's what M is about, right? So note that definition 3 makes A ring with 1. How do we do this? Well, we need a multiplication. Okay, now I'm really going to denote it times. How do I multiply 2 elements? Well, I should use M, right? Because M is meant to be some kind of multiplication. M of what? a little bit careful with the notation here. M is mapping the tensor product to here, so what I need to write is this. Okay. This is a multiplication. Well, is it? And so far I'm defining a function. Okay. What do I need to check? I'm claiming this is a ring. Right? So I need to check that these properties are that this multiplication has the right properties. So what does this tell us? It tells us that this is associative. This multiplication is associative. What else do I know? Well, this says that I have a multiplicative identity. Has a multiplicative identity. And not only do I know it exists, I know which one it has to be. It has to be U of 1. Right? I have no choice. It has to be U of 1. Because remember that in a ring, if you have a 1, that 1 is unique. Let's see. And here I found a 1, so that must be the 1. Okay? So associative and 1 are given by these two things. Okay? Does that make me a ring? Addition behaves nicely. Multiplication behaves nicely. I need distributivity. Right? Otherwise, I'm not a ring. Multiplication and addition need to behave well. So I should check that this is distributive, hopefully. So let's try to check it. Okay. What is A times B plus C? Well, by definition, this is M of A tensor B plus C. Can I distribute this? Why? That's how tensors work, right? You can distribute with tensors. A tensor B plus A tensor C. Okay. What should I do next? I need to use that M is linear, so M of something plus something. And M is linear, right? That's an essential condition here. So because M is linear, I get that this is equal to M of A tensor B plus M of A tensor C. And, well, by definition, this is A dot B, and this is A dot C. Okay. And that shows that this actually is distributive. Okay. It's also distributive on the left by the same argument. Okay. And so we checked all the properties of a ring. They all hold, and so actually this is a ring. A becomes a ring through this. Okay. And that's one of the nice things about this point of view. It's more abstract. But you see here, we never demanded A to be a ring to begin with. And it's just encoded into this picture. And it's a combination of a couple of things. One, it's a combination of the fact that our map is linear, and a combination of the fact that it's a function of tensor products. Okay? And so now, if I have something that satisfies definition 3, does it satisfy definition 2? Well, let's see. It is a ring. It has a 1. Do I have a ring homomorphism from K to A? Yeah. Do I have that U of K is in the center? Think about it and you'll see that it's pretty, that comes for free. And U of 1 is 1. Everything is true.
Did we prove that U is a homomorphism? That satisfies.
U is a. Oh, I see what you mean. U is a linear map, but we need it to be a ring homomorphism.
Right.
And so we should check that U satisfies the multiplicative law. I mean, U is also respects multiplication, and yeah, you do it. It's true. Okay. And a lot of these things, I mean, there's a lot of things to check, and you do it once, and then you see that. at least 3 implies 2. If you satisfy 3, you satisfy 2. Okay. Okay. Yep.
If we will start for definition 3 from A being a ring, will it be far more complicated to have the correct diagram?
You're saying if I started with definition 3 and I assume that A is a ring? Well, but I mean, the point is that I don't have to assume it because it follows from the other conditions. Right?
But you have to assume that it's a vector space.
I have to assume that it's a vector space.
So I think the question was, is there another way to state it where you assume that it's a ring, but you don't assume that it's a vector space?
Mm-hmm. There might be. I'm not sure if there's an easy way to do that. Okay. So that means that definition 3. If you satisfy definition 3, then you satisfy definition 2. Okay, but we need to go in the other direction as well. Suppose you satisfy definition 2. Do you satisfy definition 3? Okay. So suppose I have a ring A with 1. I have all of this stuff, and now I need to make sure that I satisfy these conditions. Okay. So I need a vector space. Do I have a vector space? Yeah. I said it somewhere, right? Yeah. I have a vector space. I need linear maps, M and U. Okay. Now I already have U. U is a ring homomorphism, and therefore it's a linear map. But I don't have M, so I need to define M. How do I define M? Well, I would like to say that, again, it's enough to define it on generators, because this is supposed to be a linear map. So what should I define? A tensor B. Yeah, sorry, M of A tensor B should just be multiply A and B. A and B and A. Okay. Is anybody worried about this? Let me give you a moment. Is anybody worried about this now?
For one thing is like, okay, maybe I missed something. Sorry. But in A tensor, are we guarantee pure tensor?
We do know that anything here is a combination of pure tensors. So if I define this for pure tensors, I define it for everybody. The issue is, and we ran into this a couple of times, that you might have A tensor B equals A prime tensor B prime. Yeah? And so we have to check this is well defined. Okay? Is this well defined? Well, let me I'm gonna insert, and this is where I'm about to really embark into a more detailed discussion of tensors, okay, and really see why this is well defined. I'm gonna prove to you in a second that this is well defined. But if you accept that this is well defined, then you'll find that everything is pretty trivial, okay, because this multiplication, being a ring, is associative, and therefore you inherit associativity. And here you're assuming that U of 1 is equal to 1, and so you inherit this picture as well. Okay? And then everything works. We get a K algebra in the sense of 3. Okay. But there's the key point. I'm kind of, it's not that I'm brushing it off to the side. I want to actually put it in center stage because this is really important, and it is, how do you define a homomorphism from a tensor product to something else? Remember the way that we define tensor products. Tensor products we define as quotients. Yeah? And whenever you have a homomorphism defined on a quotient, you have to check that this is well defined. So let's say a little bit more about that. Okay. So remember that. Okay. So now I want to discuss tensor products in more detail. Remember that we define them as follows. V and W are K vector spaces. Now we define the vector product, the tensor product, as follows. First of all, we define what's called the free vector space generated by these things. Okay, so this is K span of everything of the form V, W, where V is in V, and W is in W. So this is an absolutely massive vector space. For every pair of an element in V and an element in W, you have a basis vector. Okay. So there's a lot of basis vectors. This is very, very large. Okay.
You don't. They're not all basis vectors necessarily, because you could still have linear dependence. Like you have
So,
2W and 2V, 2W, then those aren't.
So far, I'm defining this to be what's called the free vector space on V dot, and so this is a basis, and linearity is not satisfied yet. This is just the free vector space with absolutely no relations. Okay, it's a huge vector space, but naturally we want to introduce relations. Okay, and so this is what we do. The tensor product is this thing modulo some relations. Where I is generated by the relations of linearity so what I want to say is that, for example, A plus B comma C should be the same as AC plus BC. A comma B plus C should be the same as AB plus AC. So I'm saying these are elements of this vector space, and I'm looking at the ideal generated by them, and I'm going to mod out by that ideal. Right? And so what I'm going to have is I'm going to basically introduce the relations that A plus B comma C is equal to A comma C plus B comma C, etc. You can pull out constants in either place. Okay? And I wrote this a little bit differently. when I first introduced this. But the point is that A plus B tensor C should be equal to A tensor C plus B tensor C. Okay? But I think, I mean, when I did this the other day, I said something that I didn't write, and I want to write it today. So it is that we define A tensor B, the pure tensor, to be the class of AB here. Okay? And that's the key thing here, that a tensor, an element in the tensor product, is always an equivalence class. Okay? It's always subject to all these relations. Okay? And so, warning, you could have A tensor B equal A prime tensor B prime, even though A is not A prime and B is not B prime. Because these are equivalence classes, and so it might be that these two land to be the same thing. Yeah?
So, not that this is necessarily the best way to do it, but to check well-definedness, instead of doing the normal thing, which is to start with that setup and make sure that things work out, could we just check that if we apply n to everything on the left over there, we get 0 in each case?
Basically, so yes, and that's actually what I'm about to say, and it is the best way to do it.
So we apply n if we have an defined tensor product, for example, right?
So I just defined tensor product, and it's this. Okay. So how am I going to define a map from a tensor product to something? Well, what I do is that I define it from the free vector space to L. And then I check that it quotients by I. Let me write that down. So to define a linear map, let's say M from U tensor V to W, what I do is I define M, let's say I define N of the free vector space. Okay. And I check that N of I is 0. Okay. That's always how you can define a function of a quotient. Is that you can define it on the big thing and check that it vanishes on the thing that you're taking the quotient of. Okay. Now, what does it mean to say that n of I is equal to 0? It means that n of A plus B comma C should be equal to n of AC plus n of BC, etc. Okay. So let me write that down. N of A plus B comma C should be equal to n of AC plus n of BC. N of A comma B plus C should be equal to n of AB plus n of AC. N of lambda A comma B should be the same thing as lambda n of AB, and that should be equal to n of A comma lambda B. So this is exactly what it means to be bilinear, right? This is the definition of bilinear. Yeah. And so basically, the way that you define a linear map from a tensor product to something is that you find a bilinear map from U tensor V to W. And so let me write a key theorem. Very important theorem.